So today we'll start with some applications of the Chinese remainder theorem. So CRT. So you have n, which is p times q, where p and q are integers greater than 1. And GCD of p and q is 1. So p and q are relatively prime. Then the Chinese remainder theorem says that Zn is the group Cn with addition modulo n is isomorphic to Zp cross Zq, and Cn star, which is with operation multiplication modulo n, is isomorphic to Zp star cross Zq star. Okay. So once we have this theorem, let's see how can I use this. So let's do an exercise 1. Suppose we wanted to compute 11 raised to 53 modulo 15. So note that 15 satisfies the hypothesis of the Chinese remainder theorem. So 15 is 3 times 5, where 3 and 5 are integers greater than 1 and they're relatively prime. And now I'm computing 11 raised to 53. So note that 11 belongs to Z15 star, because the GCD of 11 and 15 is 1. And we know that Z15 star is isomorphic to Z3 star plus Z5 star. So maybe I can do operations in this group here. Maybe it will turn out that doing operation in this group is easier. So let's map 11 to that group first. So we know that the isomorphism is, take any x in this, it will be mapped to x mod 3 and x mod 5. So 11 maps to 11 mod 3, 11 mod 5, which is going to be equal to 2, 1. Okay. And the operation in this group is multiplication, coordinate wise multiplication, where the first coordinate is multiplied and take the modulus, take the remainder with respect to 3. The second coordinates are multiplied and you take the remainder with respect to 5. So let's look at this. So 11 raised to 53 by the isomorphism is, it will be isomorphic to 2 raised to 53 mod 3 times 1 raised to 53 mod 5. And this part is easy. 1 raised to 53 is just 1. So I need to compute 2 raised to 53 mod 3 and 1. So I need to compute this. This is already done. So to do this, note that 2 square is 4, which is 1 mod 3. So now 2 raised to 53 is 2 times 2 raised to 52, which is 2 raised to 2 square times 26 mod 3. And here 2 square is mod 3 is 1. So this guy becomes 1 raised to 26 mod 3. So that disappears. So you just get this is equal to 2 mod 3. So which means this is 2, 1. Okay. So 11 raised to 53 mod 15, actually I should say mod 15 here, is isomorphic to this guy here, 2 comma 1. So what is the element in uh, Z15 star? Because 11 is we are now we have 2 comma 1 belongs to this. We want to go back to this. So what is the element which maps to in Z15 star, which maps to 2 comma 1? So that we can just because Z15 star has only how many elements does Z15 star have? So it has 5 of 15 elements, which is 5 is the Euler function. So we write that. So anyway, Z15 star has only a very few number of elements. 5 is the Euler function, and this is, we said, as a corollary of the Chinese remainder theorem. This is this. And 5 of 3 is a prime, so it's 3 minus 1, and this is 5 of 5 is 5 minus 1 is 4, so 8 elements. So there's only 8 elements in Z15 star, so we can just check all of them by brute force and see which element maps to this. But even when you have, there's another general method where P and Q are not very small. There's still another method which we'll see where we can go from this group here, ZP star cross ZQ star to Zn star. There is another method of doing it, even if you don't do brute force. So here, so what maps to 2 comma 1? Okay, so 2 comma 1 is, so what is X in Z15 star? Such that X mod 3 and X mod 5 equal 2 comma 1. Okay, so we can do something called unrolling. So just look at what are the integers which satisfy this equation and this equation, and we have to find an integer which maps to the same. So let's look at that. So 1, then you have 2, 3, 4, 5. So 2 mod 3 is 2, 5 mod 3 is also 2. Then 6, 7, 8. 8 mod 3 is 2. And then 9, 10, 11, 12, 13, and 14. So these are all the x's for which satisfy x mod 3 is 2. Let's look at x mod 5 is 5 is you start with 1, then 2, 3, 4, 5, 6. 6 mod 5 is 1, then 7, 8, 9, 10, 11. So you see that here there's a coincidence here. So 11 satisfies 11 mod 3 is 2 and 11 mod 5 is 1. So the answer is 11 because it's a bijection that this isomorphism here x map to x mod p and x mod q is a bijection. So as long as we find one, it is unique. It is the only one. So 11 is the pre-image of 2, 1. So 11 raised to 53. So 11 raised to 53 mod 15 is 11. Yeah. But now that we have done this, note that we didn't have to do it because if you see here, we calculated 11 mod 3 and 11 mod 5 and found it was 2 comma 1. But I've just showed you a general method, so in case you have numbers which are manageable, so these moduli are not too big, then you can do something called unrolling. You're just unrolling the modulus and see where there is a coincidence. This is a general method, but in this special case, we didn't have to actually do it. Okay, so let's do another exercise now. Suppose we want to compute 18 raised to 25 mod 35. Okay, so again 35 is 7 times 5 and it satisfies the hypothesis of the Chinese remainder theorem. So we could go through the same procedure, calculate 18 mod 7 and 18 mod 5 and do the mechanics as in the previous example. But it turns out that there is an easier way here. So remember that phi of 35 is going to be phi of 7 times phi of 5, which is 6 times 4 is 24. Okay, and we had a theorem which said that I think it was Euler's theorem. Let me just check. Yeah, it is probably Euler's theorem. It said that for a in Zn star, where n is greater than 1, a to the phi of n equals 1 mod n. Okay, so we have 24, and conveniently we have 25 here. So, and 18 does belong to Z35 star, because the factors of 35 are 7 and 5, and 18 doesn't have those factors, so the greatest common divisor is 1. So which implies that 18 raised to 24 mod 35 is 1. So which means that 18 raised to 25 mod 35 is just 18 mod 35. Okay. So I guess it's not exactly an application of the Chinese remainder theorem, but it's good to remember that Euler's theorem also, which anyway follows from the so we have used the Chinese remainder theorem here to calculate this. This followed from Chinese remainder theorem, and this followed from just Lagrange's theorem, the fact that the cardinality of Zn star is phi of n, and any subgroup of subgroup generated by an element in Zn star will have a cardinality which divides phi. This is another exercise. So the next question we want to answer is that, so how can we go from some xp xq, which is the result of computing x mod p and x mod q, to x mod n? That is, we know that Zn is isomorphic to Zp cross Zq when the GCD of p and q is 1, n is equal to pq, and p and q are integers greater than 1. So how do I go from an element here to its pre-image in a systematic manner? Because going in this direction is easy. Just give me any x, I'll just compute x mod p, x mod q, and give you this, an element in this. But how do I go in the opposite direction? So the general strategy is as follows. So we know that the GCD of p and q is 1. So find integers x and y such that x times p plus y times q equals 1. So by the definition of GCD, there must exist integers x and y such that 1 can be written as the GCD can be written as an integer linear combination of p and q. So here the GCD is 1. So we can find such x and y. So first step is to find such x and y. So now let's look at this sum here. Now if I look at xp plus yq mod p, this will be equal to yq mod p, and this will be equal to 1. Why is that? Because xp plus yq is 1. So 1 mod p is just 1. And here I'm just getting rid of the multiple of p here. So I have yq mod p is 1. But yq is a multiple of q. So yq mod q is also is 0. Because a multiple of q modulo q is 0. So that means that if I look at the integer yq modulo n, that will map to, in this set zp plus zq, it will map to yq mod p, so that we said is 1, and yq mod q is 0. So the integer yq maps to 1 comma 0. Similarly, if you look at this number here and take modulo, if you take modulo q now, so xp plus yq mod q will be equal to, this part goes away because it's a multiple of q. So you get xp mod q, which is 1, because xp plus yq was 1. So this is 1. And xp mod p is 0 because it's a multiple of p. So now we have xp mod n will map to 0, 1 in CP cross CQ. So what has happened so far? So we said that once we find these integers x and y such that xp plus yq is 1, then we have found integers yq and xp which map to 1, 0 and or should I say it again, yq and xp which map to 1, 0 and 0, 1 respectively. So now our question was that how do I go from a pair xp, xp xq and zp cross zq to this? So this xp xq can be written as, let me just turn the page. It can be written as xp times 1, 0 plus xq times 0, 1. And what I mean by this is that you just add 1, 0 to itself xp number of times. And 0, 1 to itself xq number of times. Because xp and xq are integers in this is in from 0 to p minus 1. So if xp is 0, it's, you don't have to add it even once, just let it be there. But for any non-zero xp, you just add it that many number of times, and xq add 0, 1 that many number of times. Now by the Chinese remainder theorem, now this will, we already, so what does 1, 0 map to? We found these integers thing. So we said if xp plus yq is equal to 1 for some x, y, and z, then xp mod n map to 0, 1 and yq mod n map to 1, 0. So now we have 1, 0 being added xp number of times and 0, 1 being added xq number of times. So now the pre-images, because we have this is a, there is a bijection from zn to zp cross zq. So the pre-image of xp xq is going to be, so let me write it like this. So if you have xp xq on this side, that is going to be your yq xp number of times plus xp xq number, because we said that xp xq is of this form: 1, 0 added to itself xp number of times, 0, 1 added to itself xq number of times, and the pre-image of 1, 0 is yq. So I'll add yq xp number of times, and so these are subscripts, by the way, just p and q here, and the pre-image of 0, 1 is xp. So here it's a multiple actually, so notation is misleading, but I hope it's clear from context. Anyway, the course outline has the right notation, so you can look at that. So here you add this xq number of times, x sub q number of times. Here it is the x times p added to itself, x sub q number of times. Okay. So let's look at an example. So suppose we look at n equals 35. So P and Q are 5 and 7. So the question is, what does 4 comma 3 correspond to? 4 comma 3 in Z5 cross Z7 correspond to in Z35. Okay. So what's the first step? First I have to find this capital X and a capital Y. So I have to find this capital X and capital Y such that this is 1. The integer linear combination of P and Q is 1. So here you have P is 5 and Q is 7. So you can use the extended Euclidean algorithm, but here the numbers are small. So 3 times 5 plus minus 2 times 7 equals 1. 15 minus 14 is 1. So this is the P, this is the X, this is the Y, and this is the Q. Okay. So capital X and capital Y are 3 and minus 2. So now what is XP? X sub P is 4 and uh, X sub Q is 3. So here the thing was, you just add this 4 times. What should I add 4 times? This guy 4 times. And so this is minus 14 mod 35. That is just 21. So 21 added to itself 4 times plus 21 added to itself 4 times. And XP is, so XP has to add XQ number of times, 3 times. So 15 3 times. Mod 35 is the right answer. So here this is 45, mod 35 is just 10, is 84, so that's 14. So 14, 84 is 70 plus 14, right? 70 is 2 times 35. So this is 14 plus 10 mod 35, which is 24. So 24, and we can check this. So 24, if I take modulo 5, I get 4. So 24 modulo 5 is 4, and modulo 3, modulo 7 times 3 is 21. So 24 modulo 7 is 3. So it does map. So 24 is the right pre-image of 4 comma 3. Okay. Okay. So there is an extension of the Chinese remainder theorem for more than 2 integers in the product. The modulus n was p times q, and we said Zn is isomorphic to Zp cross Zq, and Zn star is isomorphic to Zp star cross Zq star. But what if the modulus n is the product of more than 2 integers, which are all relatively prime? So the extension of the CIT is as follows. So if you have L relatively prime integers, so let's say m1, m2 up to m sub l are pairwise relatively prime. So that means that the GCD of mi and mj is 1 for all I not equal to j, and so all these integers are greater than 1. I'm not writing that, but that is implicit. and you calculate, let's say capital M is the product of all these integers. So this is going to be that modulus here. So I goes from 1 to L Mi. Then Zm is isomorphic to Zm1 times Zm2 Zml, and Zm star is isomorphic to Zm1 star times Zm2 star Zml star. Okay. And the proof actually follows from the Chinese remainder theorem. You just let's say M is a product of L such integers. First consider M1 and capital M divided by M1. It is the remaining terms. So those two are it's just a pair of integers. So M1 and the remaining uh, integers. So capital M divided by M1. So those M1 and that capital M divided by M1 will be relatively prime because of this relatively prime property of the integers. And so you can use the Chinese remainder theorem to get Zm is so the proof. Well, let me just write a few words here. I'll not do the full proof. So consider M1 and capital M divided by M1. So you argue that GCD of M1 and capital M by M1 is 1. So you get Zm is isomorphic to Zm1 times Z capital M divided by M1, and Zm star is isomorphic to capital M1, Z1 M1 star, and Z capital M divided by M1 star. And now, so after this, then consider M2. Now consider M2 and M divided by M, M1, M2. So the product of these two is going to be M by M1. So the strategy is that now you prove that this is isomorphic to Z M2 cross Z M by M1 M2, and argue that first of all. So now these two integers satisfy the hypothesis of the Chinese remainder theorem, the original one, not the extension, where you had only like a couple of integers, P and Q. So now argue that and show that, and from the Chinese remainder theorem, it follows that Z M by M1 is isomorphic to Z M2 cross Z M by M1 M2, and the star version also holds. And it'll now substituting this into this, you already get some. So Zm is isomorphic to Zm1 cross Zm2 cross Zm by M1 M2. So you keep going until you only M by M1 M2 up to ML minus 1. That will be just ML. So you get this as you keep going with this argument here. So I'm not doing it in detail, but it can be done. So it follows from the original Chinese remainder theorem. Okay, so and this means that we can solve we can solve a system of congruences of a particular form. So let's see. So suppose I want to solve something like this. Solve for x modulo 105 which satisfies x equals 1 mod 3, x equals 2 mod 5, x equals 3 mod 7. Suppose I want to solve for this. Now 105 is the product of 3, 5 and 7. So 5 times 7 is 35, 35 times 3 is 105. And so using the extended form of the Chinese remainder theorem, we want to solve for this. And I'll argue that we can solve for this. And in fact, examples like these are the reason why this theorem is called the Chinese remainder theorem. So the story goes that there was, I think it was Sun Tzu in the 3rd century AD, who Sun Tzu Suanqiang, according to Wikipedia, in 3rd century AD, who argued or who asked the question like this. He said that suppose you have some oranges, and if you group them in threes, that if you divide by 3, then you have 1 left. So you have a certain integer number of groups, each containing 3, and then there's 1 left. If you group those oranges in 5s, then you have 2 left. If you group them in 7s, you have 3 left. So how many oranges did we begin with? So he stated this, and according to Wikipedia, he did not give any proof for a algorithm, but Aryabhatta in the 6th century apparently gave an algorithm for solving this problem. And later other work in this modern form, I think, was done by Gauss in 1801. So let's solve this using this extended form of the Chinese remainder theorem. So I'll state the solution using this extended form, and then we'll solve this particular example also. Okay, so it turns out that the solution is given in this form. So let m1, m2, ml be pairwise relatively prime positive integers all greater than 1. Then the unique solution modulo capital M of M1, where capital M is the product of all these small m's of the system of congruences, x equals a1 mod 1 1, x equals a2 mod m2 up to x equals al mod ml is given by capital small x is a1 capital M1. I'll define it shortly. It is capital M y1. I'll define y1 also, plus a2 capital M2 y2 up to al capital ML yl mod n where mi, the ith capital mi, is going to be capital M, which is a product of all the small m's divided by small mi, and mi yi equals 1 modulo small m. So yi is the multiplicative inverse of capital Mi mod Mi. Okay. So what is the statement again? Let's just go over it. So you have some pairwise relatively prime positive integers all greater than 1. So this GCD of mi small mj is 1 for all I not equal to j. Then the unique solution modulo the product of all these integers of some system of congruences. So what is the system of congruences? I want x such that x is congruent to a1 mod m1, x is congruent to a2 mod m1, x is congruent to al mod ml. I think I said that correctly. X is congruent to a2 mod m2, x is equal to al mod ml. So this such an x is given by a closed form expression where this capital Mi, so m1 will be m capital M by small m1, m2 will be capital M by small m2, and so on. And y1, y2, y3 are all the respective multiplicative inverses of capital m1, m2, ml modulo m small ml, small m1, and so on. So let's look at a special case and see why this is true. Let's consider L is equal to 3. Suppose L is equal to 3. Then capital M is M1, M2, M3. And according to the hypothesis, we have Zm is congruent to Zm1 times Zm2 cross Zm3. Okay. Now we want x such that x is congruent to x mod x a1 mod m1, x is congruent to a2 mod m2, x is congruent to a3 mod m3. Okay. So we are asking for what is the pre-image of a1, a2, a3 from this set. So if I look at a1 mod m1, a2 mod m2, a3 mod m3 in Zm1 cross Zm2 cross Zm3. So we are asking what is the pre-image of this mapping here, which is the mapping which we have been using in the Chinese remainder theorem. And so the answer is they're saying it's of this form. So for the special case of L equals 3, so they're saying that the answer is going to be x equals to a1 m1 y1 plus a2 m2 y3 y2 plus a3 m3 y3 mod m, where m1 is capital M by small m1, which is m2 m3, m2 is m1 m3, and m3 is m1 m2, small m1 m2. And y1, y2, y3 are the multiplicative inverses. So let me turn the page and continue the argument. Okay. So the claim of the result is that it satisfies x congruent to a1 mod small m1, x is congruent to a2 mod small m2, x is congruent to a3 mod small m3 is given by this expression here for a special case of L equals 3, a1 m1 y1 a2 m2 y2 plus a3 m3 y3. m1 is the product of all the three small m's divided by m1. So small m2 small m3, m2 is capital M2 is small m1 small m3, and capital M3 is small m1 small m2. And y1 y2 y3 are the multiplicative inverses. So capital M1 y1 is this, capital M2 y2 is this, and so on. So let's look at what happens when I look at m1 y1. What does it map to? In Zm1 cross Zm2 cross Zm3. So the first coordinate is m1 y1 mod m1. Mod m1 it's 1. And mod m2. So note that m1 is the product of m2 and m3. So m1 mod M1 Y1 will also be a product of M2. So M1 Y1 mod M2 is 0. Similarly, M1 Y1 mod M3 will be a product of M3, so that will be 0. Okay. So that means that, and similarly, so now you can see that A1 times M1 Y1 will be congruent to A1 here. So you get A1 in the first coordinate. So similarly, M2 Y2 mod M in the, so this is in Z M1 cross Z M2 cross Z M3. So this will be congruent to 0 1 0, and M3 Y3 mod M be congruent to 0 0 1 in the same group there. So which means that A1 M1 Y1 plus A2 M2 Y2 plus A3 M3 Y3 mod M will be congruent to A1 times 1 0 0 plus A2 times 0 1 0 plus A3 times 0 0 1, which is A1 A2 A3. This means that x mod m small m1 is A1, x mod small m2 is A2, and x mod small m3 is A3. So now we are ready to solve this system of congruences modulo 105 x. Find x modulo 105 such that these three congruences are satisfied. So what is our little m1 here? 3. Little m2 is 5. Little m3 is 7. So capital M1 is capital M by M1, which is 105 by 3, 35. Similarly, capital M2 is 105 by 5, which is 21, and capital M3 is 105 by 7, which is 15. Okay. So I need M1 Y1. I want Y1 such that M1 Y1 is equal to 1 modulo 3. Now capital M1 is 35. 35 modulo 3 is 2. And 2 square is 4. 4 is 1 modulo 3. So if I choose so let's try y1 is equal to 1 doesn't work. Y1 is equal to 2 works because 35 times 2 is 70. 35 times 2 is 70. 70 is 69 plus 1. So y1 is equal to 2 works. M2 y2 equals 1 modulo 5. M2 is 21. That's already 1 modulo 5. So y2 is just 1. And M3 y3 equals 1 modulo 7. So M3 is 15. It's already 1 modulo 7. Y3 equals 1. So we have y1, y2 and y3. Now the answer is x is a1 m1 y1, a2 m2 y2 plus a3 m3 y3 mod 105. So a1, a2, a3 very easy to remember, is 1, 2 and 3. So we have m1 y1. So note that here it is modulo m. It's modulo capital M, not modulo the small m ones. So m1 y1 is m1 is 35 and y1 is 70. Y1 is 2, so this is 70, and a1 is 1. So 1 times 35 into 2 plus 2 times m2 is 21 into 1 plus 3 times a3 was 3. This is 15 into 1 mod 105. So this is so 70 plus 42 plus 45. right? So this is going to be 157 mod 105, which is 52 mod 105. And we can check if this is the right answer. So 52 divided by 3 leaves a remainder of 1. So 52, so 17 times 3 is 51. So 52 mod 3 is 1. So this guy is congruent to 1, 2, 3 in. So you can check the other two also. 52 mod 5 is 2. It's 50 plus 2. And 7 times 7 is 49. So 52 mod 7 is 3. Sorry about that. I focus on the. So this 52 mod 105 is congruent to 1, 2, 3 because it leaves the remainder 1 when divided by 3, leaves the remainder 2 when divided by 5, leaves the remainder 3 when divided by 7. So this is how we use the Chinese remainder theorem to solve it. It might seem that it's overkill because 105 is a very small modulus, so you can just look at all the numbers from 0 to 104 and just do the division and check. But when these the factors of this modulus, when they become very large, then it's very convenient to have this Chinese remainder theorem based method of solving such congruences. So now we are ready to discuss RSA encryption. So RSA stands for Rivas, Shamir, and Adelman, the three scientists who came up with this scheme. It's a public key encryption scheme. So before we define the RSA encryption method, let's look at something called the factoring assumption. Okay, so given a composite integer n greater than 1, so the factoring problem is to find integers p and q which are both greater than 1 such that p times q is n. Find p greater than 1, q greater than 1, so such that where both of them need to be integers such that p times q is n. So you want to find non-trivial divisors, because if p is 1, p or q, either of them is allowed to be 1, you can just write n as n times 1. So you want to find non-trivial divisors of n. So one can always do factoring by trial and trial division. You exhaustively just start from the integer 2 up to square root of n and keep trying to divide n by that integer. So trial division is so you just exhaustively check if p divides n for p into 3 to square root of n. Okay. So the largest integer, which is strictly less than or equal to square root of n. So I keep checking this. So this trial division has a running time which is exponential in the bit length of n. So how long does trial division take in the worst case? So trial division has running time, which is so if the order of you need square root of n steps in the worst case, and each step is a polynomial in the number of bits which can be used to describe n. So it is polylog n. So log n is the number of bits in bits which are used to represent n, and the division itself, each step in the division is in the worst case. It's going to be the running time of the division algorithm is polynomial in the bit length of n, which is itself log n. So again, this is the worst case. This is an upper bound because for the small when p is small, it will take much less time than polylog n, because it will be polylog. It'll take less time. So, but this is a good estimate. Now this is of the order of square root of n is, so n is approximately so if n is this is the bit length of n. You can say this. So if n is some 100-bit integer, then n is approximately 2 raised to 100. So n is sorry about that. So if n is a 100-bit integer, then we can say n is approximately 2 raised to 100, of the order of 2 raised to 100. So we'll say that this is of the order of 2 raised to n by 2, because we have square root of n here. So the by 2 is for that. And it is the log of n will be approximately this bit length here, and this will be raised to c. So some logarithm in some polynomial in n and the bit length of n, where here the number of bits which are used to describe n. So if you write n as a binary integer, this notation is the bit length of n. So note that this is exponential. This trial division is exponential in the bit length of n, and the input length to the trial division is going to be n. The input to the trial division algorithm is going to be the integer n. We want to check, we want to find its factors. So if we represent this n as a binary string, then the length of that string is precisely this double bar n. So the running time in the worst case is going to be exponential in the input length. So this trial division is not a polynomial time algorithm. So in general, finding factors of a large integer is hard. So this hardness is captured in something called the factoring assumption. So what is the factoring assumption? So let there be an algorithm which will output some n. Okay, so let gen modulus be a polynomial time algorithm that on input 1 power n, which is the where n is it was little n was the security parameter here, but little n here is going to be going to capture the length of the factors of n. So it outputs three integers n, p, and q, where n is equal to pq and p and q are n bit primes. So this gen modulus, it is going to generate this triple here. It's going to generate, so it's going to take little n as an input, and it's going to generate a triple which the second and the third integer are n bit primes, and the first integer is a product of these two n bit primes. But there's a catch here. So we'll say that these p and q are going to be n bit primes except with a probability which is negligible in n. So why do we have this qualification here? So gen modulus will input a triple of integers. This will be always be true. So the first integer will be the product of the second and the third. But these p and q may or may not be prime. But we want them to be they are not going to be prime with a negligible probability in n. So the reason is that when n is large, if I give you some integer and ask you to check whether it's a prime or not, so there exist polynomial time algorithms which can be used to check that. So that is a famous algorithm, which is the AKS algorithm. But in practice, people use randomized algorithms for generating primes, and those are randomized algorithms. They fail with a probability which is negligible in it. So we're going to get some integers, some n-bit integers, p and q, such that p times q is equal to n, and they are going to be prime with a very high probability. And how high? The probability that they're not prime is going to be negligible. Okay. Okay. So the factoring experiment is going to be defined with respect to this polynomial time algorithm gen modulus. I think it won't fit in this page. Let me turn it. So the factoring. So we'll call it factor. Once again, you have an adversary A and gen modulus algorithm. So the experiment is defined with respect to these two, and a security parameter. The experiment has 3 steps. The first, so you run the gen modulus with security parameter 1 raised to n to obtain npq, the triple. Then the adversary is given only the first one, only n, and it outputs p prime and q prime greater than 1. It outputs a pair of integers, p prime and q prime greater than 1. So we say that the adversary succeeds, that is the output of the experiment is 1. If n is equal to p prime q prime and 0 otherwise. Okay. So the factoring experiment, you start with the output of the gen modulus algorithm. You give only n to the adversary, and the adversary is supposed to output a pair of integers, and the adversary is said to succeed if this n is a product of these two integers which the adversary gives. So we do not use PQ here. So we are not requiring the adversary to output P and Q. We are only saying that it has to output some P prime Q prime such that the product is N. The reason for that is that if it turns out that we said that P and Q could be composite, they may be not primes with a negligible probability. So if that event happens, that P and Q are not prime, then N may have other factorizations other than this N equals PQ. Because if P and Q are not they're composite, maybe you can write N as some other factorization which is different from just P times Q. And with respect to this experiment, we have a definition. So we say that factoring is hard relative to gen modulus if for all if for every PPT probabilistic polynomial time algorithm or adversary A, there exists a negligible function negl such that the probability that the adversary succeeds, that is the factor script A gen modulus of n equals 1 is negligible. It's bounded by negl of n. So we want gen modulus to be such that factoring is hard with respect to that algorithm. So whenever gen modulus outputs a triple, you give this the first integer, the capital N, to any polynomial time adversary, and they should succeed only with a negligible probability. And this is the definition and the assumption, the factoring assumption, which was the beginning of this section here. So the factoring assumption is that there exists such a gen modulus with relative to which factoring is hard. So the factoring assumption states that there exists an algorithm which can generate such n's and p's and q's such that factoring is hard, so that no other adversary. So if the gen modulus gives you primes, then we are basically saying that p and q, if gen modulus the p and q generated by gen modulus are prime, then we're basically saying that it's very hard to do factoring. But even if the gen modulus gives you composites, when p and q are composite, so we are saying that polynomial time adversary will not be able to exploit that weakness of gen modulus. So relative to which factoring is hard. Okay. So now we are ready to define the plain RSA. So we'll this factoring assumption we'll relate it to something called the RSA assumption. But before we can discuss the RSA assumption, let's just first look at RSA itself and see how that works. So I'm going to describe some a flavor of RSA which is called plain RSA. So the reason it's called plain RSA is that it's a deterministic form of the RSA scheme, and it is because it's a deterministic encryption scheme. It's not secure because as we learned before, so it is not going to be CPA secure. But there are variations of this So you can add some extra algorithms to the RSA scheme to make it even CCA secure. But for our purposes, let's begin with the simplest form of RSA, which is the deterministic form of RSA. So for that, we'll need again a PPT algorithm, which we'll call it Gen RSA. Let's say let Gen RSA be a PPT probabilistic polynomial time algorithm that on input 1 power n outputs a modulus Kaplan, that is the product of two n bit primes along with two integers, along with integers e greater than 1 and d greater than 1, satisfying ed equals 1 mod phi of n. Okay, so now we want Gen modulus was giving us a Kaplan and a pair of integers p and q, such that n is equal to pq. But here Gen RSA we want that n to be a prime of two n bit primes. The difference is that Gen modulus, that product that p and q could be composite numbers with a negligible probability. So, but here we are saying we have definitely want n to be a product of two n bit primes, and in addition to that, we want the Gen RSA to give us these a pair of integers e and d, which are both greater than 1 and which satisfy this. So we'll see that in the encryption scheme, this e is going to play a role in the encryption part of the algorithm or the scheme, and the d is going to play a part in the decryption part of that. Hence the choice of notation. Okay. So let me turn the page now. So we want e greater than 1, d greater than 1, such that e times d equals 1 mod phi of n. Right. Now if we choose e greater than 1 such that GCD of e and phi of n is 1, right? Then the multiplicative inverse of e exists by the lemma we saw before, or the proposition we saw before. In modulo phi of n, the multiplicative inverses exist for integers which have a GCD of 1 with phi of n. So if the GCD of e and phi of n is 1, then a multiplicative inverse will exist, modulo phi of n, and d can be that. So the multiplicative inverse will play this role of d. Multiplicative inverse of e will play the role of d, will satisfy the condition required by d, which is ed equals 1 modulo phi of n. So the multiplicative inverse of e in z phi n star. So So let me write it here. So D is the multiplicative inverse of E in Z. So the modulus is now phi of n, because we want this ED equals 1 mod phi of n, not mod n. Okay, so let's say we have this. So we have n, a modulus, which is the product of two primes, and then we have this E and D such that ED equals 1 mod phi of n. Okay. So the public key encryption scheme is going to have these three algorithms: gen, enc, and dec. So let's define a public key encryption scheme. As follows. So first, gen, key generation algorithm. So on input 1 parent, run gen RSA on 1 parent to get N, E, and D. So the public key is this. It's just the pair NE, and the private key is ND. Okay. I'm using angle bracket here, but you can use parentheses also. So nothing special about it. And the enc, the key encode, the encryption is, so the public key can be shared, can be made public, as the name suggests. So this, if I want to receive some information from some sender, I just publish my public key. I make it public. So I publish the modulus and the encryption exponent, as it will be called, the E. But I'll keep this D secret here. And anybody who wants to send me an encrypted message will use this N and E pair to send me the message. So how do they do that? So on input, a public key PK NE and a message M in Zn star. So we need the message to be an integer in Zn star. So it can't be some arbitrary bit string. So if you have arbitrary bit string message, you need a way to map it to an integer in Zn star. So you compute the ciphertext C equals M to the E mod N. So you take the integer, which is the message, you raise it to the eth power, and since this is M belongs to Zn star and you're doing multiplication, C will also belong to Zn star because you're doing M to the E mod N. Okay. Finally, the decryption. So it will use the ciphertext and the secret key, which consists of N and D. So in fact, N is public. The secret part is the decryption exponent D and ciphertext. And given a ciphertext C in Zn star, output M hat as C to the D mod N. Okay. So the encryption is just M to the E mod n, and the decryption is C to the D mod n. So let's see, is this a valid encryption decryption scheme? For it to be valid, if I encrypt M and I decrypt using this method, I should get back M. So do I really get it back? Let's check that. So if C is equal to M to the E mod n, what is M hat? M hat is C to the D mod n, which is M to the E whole raised to D mod n. Now, what is E times D? Now, E times D, we said, was 1 mod phi of n. So this is equal to M to the ED, which is some integer k times phi of n plus 1 mod n. Because E times D was 1 mod phi of n. So it is some integer multiple of phi of n plus 1. Now, but M belongs to Zn star. So by Euler's theorem, M raised to phi of n is 1. So this is M raised to phi of n whole raised to k times M mod n. This is 1. So it's 1 raised to k, it goes away, and you just get back your M mod n. So your decryption of the encrypted ciphertext gives back the message. Okay. Now, so where is the factoring coming in? So the main secret here is the factorization of n. So here we said the secret key is D, but if you know the factorization of n, then you can find D. Why is that? What is D? D is the multiplicative inverse of E in Z phi of n. And what is phi of n? Phi of n, if n is equal to PQ, phi of n is P minus 1 into Q minus 1. So somebody who does not know the factorization of n cannot compute phi of n from n. Because if I know the factorization of n as PQ, then I know that phi of n is P minus 1 into Q minus 1. But if I don't know the factorization of n, I don't know this phi of n. I can't compute phi of n. And if I can't compute phi of n, I won't be able to compute the multiplicative inverse of E in Z phi n star. Because I won't know what phi of n is, so I don't know what D is. So E, which is the encryption exponent, it's going to be made public. The adversary can only see E. But the valid receiver, he has D, because he knows, either he knows phi of n, or either he knows phi of n or he has D. And actually those two facts are equivalent. Knowing phi of n is the same as D, we'll see later. So the main secret here is the factorization of n. Because if this was not secret, then from the encryption exponent, which is in the public key, an adversary could compute or can compute the decryption exponent. So here, an adversary who sees C, if he knew the factorization of n, he can just compute the multiplicative inverse of E mod phi of n, and then that will be D, and he can just decrypt the message and this form. Okay, so we'll let's stop here, and we'll look at an example of this numerical example of RSA in the beginning of the next lecture, and then we'll continue with the rest of the topics.